In this video, we'll give a brief overview of our paper, Decoupled Dynamic Filter Networks. First, we give a brief introduction of convolution. Convolution is a cornerstone of existing convolutional neural networks, which are tremendously successful in several computer vision tasks, such as image classification, object detection, and semantic segmentation, to name a few. Despite its common use, standard convolution has two main shortcomings: content agnostic and computation heavy. Consider these rows in image. The same convolution filters are applied to all pixels in a sliding window manner. Also, once the CNN is trained, these filters are fixed and applied across different images. Given the varied nature of scenes, this filter sharing across pixels and images may not be optimal for future extraction. Being computation heavy is another shortcoming. As we illustrate here, a set of convolution filters contains C' by C by K by K parameters. Its computational costs increase significantly with the increase in the channel number C and C'. This poses a significant problem, as convolution layers in modern CNNs have hundreds or even thousands of channels. To tackle the content-agnostic issue, several dynamic filters are proposed in the literature. They usually leverage separate network branches to predict content-adaptive filters. However, these methods further increase the number of parameters and computational costs, because the generated tensor at each location is a complete convolution filters corresponding to that pixel. For the second issue, grouped and depth-wise convolution are usually employed to reduce the parameter number and computational cost, but directly using these alternatives usually results in a performance drop. To retain a similar performance with these alternatives, one needs to considerably increase the number of future channels, which will lead to more memory consumption and longer memory access time. The goal of this work is to design a filter operation that is content adaptive while being lighter weight than a standard convolution. Realizing both properties with a single filter are quite challenging. We accomplish this with our decoupled dynamic filter, where the key techniques is to decouple the dynamic filters into spatial and channel filters. In particular, we first predict spatial and channel filters individually via two side branches. When processing filters as ith pixel and rth channel, we first select and rearrange the corresponding ith spatial filter from the predict spatial filter tensor. Second, we rearrange the predict channel filter tensor, where we select the corresponding rth channel filter. Then, we combine the selected spatial and channel filters by element-wise multiplication. At last, the multiplied filter is applied on the neighboring area at ith pixel and rth channel to obtain the output. We implement the entire DDF operation in CUDA as a single layer. This eliminates the need to save intermediate multiplied filters during network training and inference. We designed two lightweight attention-style prediction branches to predict spatial and channel filters, ensuring that the entire DDF module is also efficient. The spatial filter branch only contains a one-by-one convolution layer. The channel filter branch first uses a global average pooling to spatially aggregate filters. Then it adopts a squeeze and excitation structure to generate channel filters. Here we compare the inference latency and running memory between convolution, depth-wise convolution, dynamic filter, and our DDF module. We choose PAC as a representative of dynamic filters. Inference latency and running memory are evaluated on a mini batch with 2 by 256 by 200 by 300. DDF has much lower computational cost compared with PAC. Also, it is even computationally cheaper than a standard convolution layer. To demonstrate the use of DDFs as a basic building blocks, we experiment with the widely used ResNet architectures for image classification. We switch the 3x3 convolution layer in the basic and bottleneck block with DDFs, and keep the original hyperparameters, especially using the same number of channels. As we can see, DDF ResNet surpassed ResNet 50 and ResNet 101 by 1.9% and 1.3%, while the computational costs are reduced by nearly half. Also, DDF ResNet surpassed other ResNet variants. Moreover, we extend the use of DDF to typical and joint upsampling networks. The typical upsampling task enlarges the input image or feature map. The joint upsampling tasks enlarge the image or feature with the given high-resolution guidance. An advantage of dynamic filters compared with standard convolution is that one could predict dynamic filters from guidance filters instead of input filters. Following this, we propose the DDF upsampling module, which can be used in both typical and joint upsampling scenarios. We name this module DDF up. As illustrated in figure, when the upsampling factor is 2, DDF up employs 4 DDF operations. All of them use the channel filters predict from input and the special filter predict from the guidance. For the typical upsampling case, we compute the guidance filter from the input filters using a depth-wise convolution layer. DDF up can be seamlessly integrated into several CNNs where upsampling operators are needed. We present two applications in object detection and joint depth upsampling. In object detection, we embedded DDF up into the top-down path of FPN for future upsampling. In joint depth upsampling, we use the similar network architecture as PAC-net, where we employ our DDF up modules to replace the PAC joint upsampling modules. As shown in table, DDF up surpass standard CNN techniques like DJF and DJF+ by a large margin. DDF up also improves over dynamic filtering PAC-net by relatively 10% while reducing computational cost with an order of magnitude. We also visualize 16 times upsampling results, where we can see that DDF up recovers more details compared to PAC and other techniques. In summary, we propose the Decoupled Dynamic Filter, DDF, and its upsampling variants, DDF up, in this paper. They are content adaptive, fast, they have small memory footprints, bring consistent performance improvements, and can be used as a basic building blocks of CNNs. Thank you for your time.